Hi everyone, this is Iman and welcome back. In today's video, we're going to look at torsional irregularity in buildings, what it means in the context of ASCE 7, how to calculate it, and finally, how to check it in ETABS. Let's get started.
All right. According to ASCE 7, torsional irregularity is evaluated using the torsional irregularity ratio, or TIR, which is delta max over delta average. Okay. Looking at this plan view, you can see a solid rectangular, which is the story that we are going to check its torsional irregularity, and the dashed line over here, which is one floor below. Why? Because per code, when you are checking torsional irregularity, you have to calculate story drifts. And I'm sure that you all know what's the definition of a story drift. It's a relative displacement between two adjacent floors. So that's why we have to check the story below. Okay. So delta max is the maximum story drift at the building's edge, and delta 2 is the story drift on the other building's edge, and delta average is obviously it's the average of these two values. Okay. Now, based on the value of this ratio, the code classifies the building in three categories. If TIR, this ratio, is bigger than 1 and less than or equal to 1.2, this building is regular. If the ratio is bigger than 1.2 and less than or equal to 1.4, the building is classified as torsional irregular. And if it's bigger than 1.4, the building has an extreme torsional irregularity. And very important note, when you're checking the torsional irregularity, make sure to use the equivalent lateral force procedure. Because in dynamic analysis, the maximum displacements don't occur at the same time. So we have to make sure we're using a static analysis, which is the equivalent lateral force method. Okay. All right. Before we get into ETABS, let's quickly go over some important notes about torsional irregularity. Number one, this study only applies when the diaphragms are rigid or semi-rigid. Flexible diaphragms are not considered here. Number two, when calculating the story drifts, if you have a semi-rigid diaphragm, the code allows you to assume it's rigid for the purpose of torsional irregularity checks. Number three, points that are not part of the lateral force resisting system are excluded. For example, cantilevers or overhanging slabs are not to be included in the torsional irregularity check. Number four, the check must be done without P delta effects included, because we're looking only at the lateral displacement from the applied seismic force. And number five, this one is very, very important. If torsional irregularity is triggered as even one story and under only one of the four accidental eccentricity cases, that's plus minus EX plus minus EY, then the entire structure is classified as torsionally irregular. All right. So keep these 5 points in mind as we go into ETABS, because they will help you avoid common mistakes. All right. In the first example, all floors are typical. Okay. And if I right click over here, my diaphragm is D1. And if I go to define diaphragm, as you can see, the diaphragm is defined as a semi-rigid diaphragm. Okay. So what I need to do is I have to assume the diaphragm is rigid, because I'm checking the torsional irregularity, and per code we are allowed to do that. Okay. So the first thing I do is save a copy of the original model. Torsional irregularity check or ratio. So I go to define diaphragm and set it as a rigid diaphragm. Okay. Now, my approach is to first verify torsional irregularity manually and then compare those results with what ETABS reports. Okay. Now, let's say we're going to check the seismic load in the y direction at the, this is story 5, let's say at story 3, a middle story. Okay, so the first step is to consider the end edges of the plan that are parallel to the direction of the seismic force. So if the earthquake is in the y direction, we look at these two edges parallel to y. But if you're studying the earthquake in the x direction, consider this edge and this edge parallel to x. Okay, and remember, according to ASCE 7, internal nodes are not considered. Just let me go back here. You can see here the code says at the two ends of the structure. Okay. All right. Now I run the analysis. Okay. Before I jump into results, let me quickly show you the load patterns. I have the dead load, live load, and more importantly, EX, earthquake in the X direction. You can see I have selected EX, positive eccentricity, EX, negative eccentricity. Then make sure you to choose all of these three options, and I assume 5% eccentricity ratio. Okay, and similarly for the Y direction, I have EY, positive eccentricity, and EY, negative eccentricity. Okay. All right. Let's jump into results. Okay, and actually, let me take a screenshot real quick, and I'm gonna label the corners. Okay, so for example, I'm gonna call this corner as A, this as D. Let's say this is B, C, J, and L, for example. Okay, so what I need to do is to calculate the drifts for this joint and this joint, joint A and joint D, because I'm gonna evaluate the seismic force in the Y direction. So I need the story drift for this point and this point. Okay, so I select joint A, story 3. We're evaluating the torsional irregularity at the story 3. So I selected this joint. You can see here one joint selected, and then I go one floor below. Why? Because I'm gonna calculate the drift. So this is story 2, joint A, and now I go to display, show tables, and from here I am going to select joint displacements, and I'm studying earthquake in the Y direction, so I select EY, and yeah, no other setups. Okay, all right, hit OK, and this gives me the joint displacement for this joint. Okay, so I'm gonna export this to Excel. Okay, perfect. Let me grab this screenshot over here. Okay, perfect. And let me take another screenshot over here. Okay, great. Now, okay, so far I have joint A's information and outputs. Now I'm going to capture the joint displacement for joint D. Okay, so again, hit escape on the keyboard. So now I'm going to select joint D. Okay, we are at story 2, so I am going to go up. So story 3 is story 2. I selected joint D. Again, display, show tables. Okay. And actually, I am going to copy this and go to ETABS and select all this info. Come here and paste. So, all right, this is the story 3 relative to a story 2. Story 3 relative to story 2. So this is for joint A, and this is for joint D. Okay, joint A, joint D. All right, now I can easily calculate the delta values, and my unit is inch. Okay, so all right, you can see there are 3 cases here. We have 3 step numbers, 1, 2, 3, 1, 2, 3. Okay. So these are basically earthquake in the y direction, EY plus eccentricity, and EY minus eccentricity. Okay, we have 3 cases. All right, for the step number 1, I'm going to calculate delta, which is in the y direction. So it's UY, right? It's equals this cell minus this cell. So this is for story 3, this guy is for story 2, and they are related to the same step number. Okay. All right, I'm gonna drag this. So, okay, and step number 3. Okay, perfect. I'm gonna copy this and paste here. Let's double check. They are following the same pattern. Yes. And yes, that's correct. Okay, great. Okay, now I can easily calculate delta 1, delta 2, and their average. So let me move these pictures a little bit over here. Okay, we have 3 step numbers, 1, 2, 3, and for each step number, I'll calculate delta 1, delta 2, and delta average. Okay. All right. For the first step number, this guy and this guy, number 1, number 1. Okay. The maximum is max this, comma this. Okay. And delta 2 is the displacement on the other edge, which is the minimum of this and this, because we're still in the step number 1. Okay. And I can easily calculate the average of these 2 values over 2. Okay. And then TIR is delta max over delta average. Okay. And similarly for step number 2, minimum and the average. Okay. All right. And step number 3. Oops. Okay, perfect. All right, great. these ratios can also be read directly from ETABS. Okay, and my goal is to verify ETABS calculations with our calculations in the spreadsheet. So I go to display, show tables, under joint output displacement, and there are two options over here: diaphragm maximum over average drifts and story maximum over average displacement. So make sure to select this one. Otherwise, nodes that are not connected to the diaphragm, such as ramps or cantilevers, will be included in the displacement output, which leads to incorrect results. Okay, make sure to check diaphragm, not story. Okay, and over here, looking at the third floor results for an earthquake in the y direction, because we're studying story 3, you can see the ratios over here. So we see two ratios greater than 5, this one and this one. These are clearly software errors. So because under EY, in addition to displacement in the y direction, there is also a small displacement in the x direction due to torsion. So the software mistakenly checks delta x, which are extremely small, and ends up dividing two small numbers, two numbers close to 0. Okay, which produce artificially large values. So the fix is simple. Filter the item column, so only y direction is considered. Okay, I select y, and if I go here, story 3, yeah, you can see those values are gone, the big values. Okay, and actually I'm gonna copy these 3 ratios, copy and paste over here. As you can see, the ratios reported by ETABS line up perfectly with our manual calculations: 1.426, 1.338, 1.504. Okay, great. And similarly, you can do the same process for the earthquake in the x direction and for a different story. So we studied story 3, so you can do for all stories, and you have to do that basically. Okay. All right, let's move on to the second example, where all floors are typical except for the second floor, which has a completely different layout. Okay, essentially functioning as a mezzanine. So whether a mezzanine should be treated as an independent floor is a separate discussion, and I won't go into that today. All right. Okay, I'm gonna run the analysis. Okay. Now let's check torsional irregularity for the highest floor, which is story 5. Okay. So again, I have to calculate the joint displacement for the corners, because I am going to study the earthquake in the y direction. So these two edges are important for me. Okay, so I've already labeled the corner joints. So for story 5, I need to capture and extract the displacement at joint A and joint I. Okay, very similar to the first example. Let me do it real quick. We are at story 5. Okay, and then I go one story below, and then Control T. Yes, EY. Okay, joint displacement, and I'm gonna copy these results. This is a story 5 relative to a story 4. Okay, and I'm actually using the spreadsheet from the previous example. Now for joint I, okay, deselect, select joint I, and then we are at story 4, go to story 5, select, 2 joints selected, okay, Control T, and hit OK. Copy and paste here. Okay, I've got these values as torsional irregularity ratios. Okay, so let's see if ETABS captures the same. We are studying story 5, so you can see these values, and all of them are filtered for diaphragm in the y direction, because we're studying the earthquake in the y direction. Okay, so I'm gonna copy these 3 values for story 5, copy and paste here. Okay, 1.76, 1.46, 1.328. As you can see, ETABS results match perfectly with our hand calculations. Okay. All right, now let's check the 3rd floor, because story 2 is a mezzanine and it's a little bit challenging. So let's see, what should we do in this situation? Okay, a couple of notes. First, keep in mind that columns not connected to diaphragm are modeled as a single element. So, I mean, this is grid line 5. If I go to elevation 5, so we have a mezzanine over here. So these columns, this one, this one, this one, they should be drawn as one element. Okay, so if you have 2 elements, 2 columns, make sure to join them. So you can either delete these 2 and draw one column. Let me unlock the model. Okay, so yes, you can select these 2 columns and then go to edit frames and use joint frames option. So that way ETABS will merge these 2 as one element. Okay, now I've already done this. So yeah, if you select these, you can see only one frame selected, one frame. Okay, all right. Let me go back to the plan view. So another important note here, we need to be careful to select the nodes on the 3rd floor that correspond to the corner nodes of the 2nd floor to ensure accuracy. So what are the corner nodes at story 2? This guy, this one, and this one. So I have to make sure to select the corresponding nodes at story 3. Okay, so if I go here, the labels in orange are related to the edge nodes for story 2, the mezzanine. B, this joint, F, K, and L. Okay, B, F, K, and L. All right, let's select this and select again this one, B, B. You can see here. Now, I didn't run the model, so let's run the analysis again. Okay, so PS B on the 3rd floor and on the 2nd floor, and in the 3D view we can see them. Okay, now I go to display, show tables. Okay, displacements, and I'm gonna copy this information. Okay, and this is for joint B actually, so I'm gonna edit this, and now I'm repeating the process for joint F. Okay. Okay, escape. Now select F. Go to story 3, F. You can see here, Control T, and okay. And paste here. Okay, now this time is story 3 basically. Okay, so I have new ratios over here, here, and here for different step numbers. Okay, let's go back and see what values ETABS gives us for story 3. So these 3 ratios. Okay, I'm gonna copy these 3 and paste here. Okay. All right, as you can see in this case, manual results differ from ETABS. Okay, so basically ETABS reported larger displacement values, which is due to the large opening on the second floor. Okay. And from an engineering judgment perspective, I also prefer to compare the third floor directly with the first floor, because the second floor behaves more like a mezzanine. Okay, so what I need to do is to again select this one on the third floor and go to the first floor and then capture the displacement, and then select the I node over here on this first floor and go to the third floor, select this one at the corner, and repeat the process and calculate the TIR. Okay, so that way you can make sure that you've captured all different conditions, because again we have a mezzanine over here, and it's I think important to check the relative displacement between the third floor and the second floor and the first floor, and this one is not reporting in ETABS directly, and you have to go through the process manually. Okay. And finally, I've got the results of another example, the third example, and you can see the ratios for the earthquake in the X direction and for the Y direction. Okay, and I have the ratios in this column, and if I go here greater than 1.2, okay, so you can see in all cases the ratio is less than 1.2 except for this case. Okay, and as I mentioned in the introduction, note number 5, if the ratio exceeds 1.2, even a single story and in only one direction, the entire structure must be classified as having torsional irregularity. Okay, and a structure with torsional irregularities must comply with the specific code requirements. For example, the design forces for collectors and their connections must be increased by 25% per ASCE 7. Okay, and last point, as I mentioned in the introduction, remember not to use dynamic analysis to check torsional irregularity, because again, in dynamic analysis, the maximum displacement don't happen at the same time. All right, that's it for today's talk on torsional irregularity. If you enjoyed this, please like, share, and subscribe to support the channel. Thanks for watching, and I'll see you next time.